Okay, so we just got done with the unit on the applications of integration. You can use them to find, volumes and arc lengths and all that stuff. The unit that we're starting now is going to be based on different integration techniques. Still, there will not be any new functions or new integrals or anything like that, but it's just sort of how to deal with maybe combinations of those functions that you haven't seen before, but still no new functions. And we're just going to start with the section that covers basic integration rules. This goes past, of course, the basic integration rules that we sort of covered in the very beginning of the semester. We're basically going to look at how does an integral look, and how can you tell from what it looks like what the proper way to integrate it is. Okay. You don't actually have to. I mean, I guess you could write some of these down if you wanted, but these are the same ones that we covered in the very beginning, and that you would have learned in Calculus 1, except for these last three. So again, you don't have to write these down. I'm just going to run through them as a list. There's a constant multiple rule. If you have a constant multiple inside the integral, you can take it out or put a constant multiple inside the integral from the outside as freely as you want. If you have an integral with multiple terms in the integrand, you can split that up into separate integrals. The integral of du is u. Or in other words, well, it's u plus c. Or in other words, the integral of 1 du. Right, du is 1 du. That's u plus c. So you can also think of it as the integral of 1. This is the power rule. It's the opposite of the power rule for derivatives. If you have a variable to some power, with the integral of that with respect to that variable, you add 1 to the power and then you divide by the new power. So let's say you have u to the n. You're going to add 1 to that power, making it u to the n plus 1. And then you're going to divide by that new power, n plus 1. And all of these are going to have a plus c because they are indefinite integrals, as opposed to integrals with a lower and upper bound, where you're actually trying to find a specific area underneath the curve. These are just indefinite integrals. Okay. And the power rule only works if n is not equal to -1. It can be literally anything else, but it can't be -1. And the reason for that is because if the power was -1 and you tried applying this rule, you would raise the power up to 0 and then divide by 0, so you can't actually do that. If n is -1, then what you actually have, if u to the -1 would actually be 1 over u. And if you have that, then what you have is actually this. This is du over u, or you can also think of it as 1 over u du. And if you have that, and only if you have that specific power of u, then the integral of that is the natural log of the absolute value of whatever is on the bottom. This is a big one to remember. Okay. The integral of e to the u is e to the u, just as the derivative of e to the u is e to the u. This one's not as important, just because you don't see it as often. If your base is something other than u, then you just have to throw in a factor of 1 over the natural log of that base. So, if you had 2 to the x, the integral of 2 to the x would be 1 over the natural log of 2 times 2 to the x. The integral of sine is negative cosine. The integral of cosine is positive sine. the integral of tangent is the negative ln of the cosine. And the reason for that is the integral of tangent is actually, say tangent of u, sure, du. Tangent is actually sine over cosine. And there's a u substitution that's possible here. You have cosine on the bottom. Now the derivative of cosine, right? So if cosine was your, u, so to speak, then your du would be negative sine, which is very close to what we have up here. So I'm just going to throw in a negative sign here and balance it out by having a negative sign on the outside. Now, in fact, let me just write x instead, just so it's not weird when I talk about u and du. Okay. Now we have something on the bottom with its own derivative on the top, and that actually sort of fits this form, du over u, right? Du is that negative sine of x dx. The u that's on the bottom is the cosine of x. So this is negative the integral of du over u, which is, according to that formula, then, and there's still that extra negative sign on the outside, but it's going to be negative the natural log of the absolute value of u plus c, which is the negative natural log of cosine plus c. That's just, where that comes from. So if you ever can't remember what the integral of tangent is, if you can remember that this is the way that that integral is derived, you can always just come up with it yourself, without having to refer to anything else. It just breaks down tangent into sine over cosine, then does a u substitution with having to add a negative sign inside and outside. The integral of cotangent is the positive natural log of sine, and that's derived in very much a similar way, except it's even simpler technically, because the negative cotangent is the same as, it's not the same as, the cotangent is literally defined as being cosine over sine. And you don't even have to throw in a negative sign. You have sine on the bottom, and you have its derivative on the top. So that's enough to say, okay, well that's the natural log of whatever I have on the bottom, plus c. The integral of secant is the natural log of secant plus tangent, and the reason for that is if you start off with the integral of secant, let's just say secant of x, and there's not really anything that's very obvious to do with that. But if you take this and you multiply it by 1 in the form of secant plus tangent over secant plus tangent, just imagine there's a dx that's actually, well then that becomes on the top you're going to get secant squared plus secant tangent. And on the bottom, you're just going to have secant plus tangent. Okay. Now that doesn't look like much, but now the bottom is secant plus tangent, the derivative of which, well, the derivative of secant is this secant tangent, and we have that up here. The derivative of tangent is secant squared, and we have that over there. So actually, this again fits the form of something on the bottom with its own derivative on the top. So I guess we can say, this is u. This here is du. So this just becomes the integral of 1 over u du, or du over u, which is still the natural log of whatever that bottom thing is plus c. So the natural log of that thing on the bottom, secant plus tangent. Plus c. So that's where that comes from. As for how any reasonable human being would figure to multiply secant by secant plus tangent over secant plus tangent, that's not something I can answer, but it works. So the cosecant would happen the same way. It's just a cofunction of secant, so you can just sort of use the same tricks. Using the cofunctions cosecant and cotangent instead of secant and tangent, but fundamentally it would work the same way. These four are actually just these are just like the reverse of various derivative rules. The derivative of tangent is secant squared. So taking that backwards, the integral of secant squared is tangent. Same thing with cotangent. The derivative of cotangent would be negative cosecant squared. So the integral of cosecant squared is negative cotangent. Secant tangent, the integral of that is secant because the derivative of secant is secant tangent. And then the same thing for this last one, just with the addition of a negative sign, because there's an extra negative sign in the derivative when you're talking about cosecant. And then these three we learned most recently. Okay, so these are the integration rules that we're going to be using for the rest of the semester. Probably the most important ones are going to be this power rule, this 1 over u du rule. That's a big one that appears a lot as a form of u substitution. This one's not hard to remember, but sure. And then there's just a bunch of various like trigonometric ones. But yeah, most u substitutions will be one of these forms. either the power, the 1 over something, or e to the power of something. Is Alright, so we're going to look at a series of 3 integrals that only differ by a little bit, and hopefully through that you can sort of get used to the idea of seeing little differences in one integrand compared to another that sort of tells you the different ways in which they should be integrated. All right, so we're going to look at the integral of 4 over x squared plus 9, then the integral of 4x over x squared plus 9, then the integral of 4x squared over x squared plus 9. Now these only differ by the power of x that's on top. The first one has no x, so like a power of 0. The second one has a power of 1 for that x, and the third one has a power of 2. So this first one, with no x on top, it's just 4 over x squared plus 9. It's not a u substitution. Or like, can't really say how it would be a u substitution, because there's no choice for u that I can make from within the integrand that has its du. So for example, if I had u equals x squared plus 9 in here, then du would be 2x, which I don't have, and I can't just throw an x in there just because I want to. So u substitution probably won't work here. What will work is probably first taking that 4 to the outside, so that I have 1 over x squared plus 9. And you don't have to take the 4 to the outside, but the idea is that it'll make it easier to see. This is one of those integrals that integrates into an arctan. Just a constant on top and some sort of quadratic on the bottom. It's not an arcsine or an arcsecant just because there's no square root involved on the bottom there. It's just 2 squares being added together. One of them is a variable square, the other one's a constant square. So this is one of those arctan integrals with the variable term being x and the constant term being 3. Right, because this is, it's the arctan is what integrates into arctan is 1 over u squared plus a squared du. And no u substitution necessary, because if u is x, then du is dx, which I already have. I already have a dx up there. It's all there. Like, I don't need to throw in any constants or take any out or anything like that. So this is simply 4 times 1 over a, so 1/3, arctan of u, which is x, over a, which is 3, plus c. You can multiply the 4 and the 1/3 if you want. Yeah, sure, let's go ahead and do that. So it's 4/3 arctan of x over 3, plus c. Okay, so the second integral, it's clearly not going to be an arctan because that's what the previous one was, and this one is definitely different to that. It's usually not the case that you can take two different things and have them integrate into the same thing, so this probably is not an arctan. What it could be, though, is a simple u substitution. You know, and obviously after we do the u substitution, we will then have to use like one of the other like regular rules. But it might be a u substitution because if you think of this as a composition of functions, you know, there being some sort of like inside function on the inside of some outer function, the innermost function kind of looks like it would be that x squared plus 9. So if we allow that to be our u, if u equals that x squared plus 9, then what that means is that our du, if we were going to do a u substitution, would be 2x. Which this time, as opposed to last time, we do have an x on top, so we don't, you know, so we're able to probably do this. And sorry, du is 2x dx. That dx is important. So, you know, we have something very close to 2x dx on top. We have 4x dx. So you can either take that 4, put it to the outside, then toss in a 2 on the inside and divide by 2 on the outside, ultimately giving you like a 2 on the outside and then 2x dx on the inside. Alternatively, you can just factor out, not the whole 4, but you can just factor out 2. So just factor out 2, and you'll have 2 times the integral of 2x dx over x squared plus 9. Okay, so now this can be u. And this 2x dx that's up here now, instead of 4x dx, this can be our du. So this is 2 times the integral of du over u. Or 1 over u, du, if you prefer. And if we just go back here, that should integrate into the natural log of the absolute value of whatever u is, whatever that thing on the bottom is. That should go on the inside of a natural log. That's the integral. So like that natural log rule is is one of the rules that's just hiding a lot. Like a lot of things turn out to be du over u. But so this should integrate into 2 times the natural log of the absolute value of u plus c. Right, once you actually do the integration, there's always that plus c. And after you integrate, you are free to switch u back into terms of x, which, you're not just free to, you should. So that's 2 times the natural log of that x squared plus 9, because that was what u was. Okay, so this one ends up being a completely different function once integrated. Not an arctan, but a natural log. All just because of and a completely different integration technique. All because of that difference of that x being on the top versus there being no x on the top. Okay. Now the last one, which differs from the others by having x squared on top as opposed to x, or as opposed to no variable at all. Now this, the first thing to notice is that the power of the numerator is now at least the power of the denominator. And when that happens, so if the power of the numerator is greater than or equal to, in this case it's equal, if it's greater than or equal to the power of the denominator, then do polynomial division. Okay. Now, you don't have to write this next part that I'm going to do down because I'm just going to erase it later. So the point is to do polynomial division, and you can try to get clever with it, and instead, try to do something like let's say you take that 4 to the front, and then add 9 and subtract 9 from the top. Don't actually, you can write this down if you want to, I guess. You can do that, after which you can group these together, and then have a separate integral for these together. So x squared plus 9 over x squared plus 9, and then minus 9 over x squared plus 9. And that way you don't have to do any division, but you just gotta be really careful and have a sort of good vision of like what it is exactly that you aim to do. Also, this is going to simplify to 1. Right, because it's just the exact same thing on the top and the bottom. So it's going to be 4 times the integral of 1 minus 9 over x squared plus 9. Okay. I'm going to erase this in a little bit so that I can actually do literal, like, polynomial long division, which you probably haven't seen since algebra. Since algebra. But we are going to get the same thing. We are going to get, well, I guess if you distribute the 4, we're going to get 4 minus 36 over x squared plus 9. But that's what we'll have. Okay, so we're going to just try to rewrite this integrand by performing the actual division, 4x squared divided by x squared plus 9. So 4x squared is the dividend, and x squared plus 9 is the divisor. Okay. X squared fits into 4x squared 4 times. So 4 goes up here. After which we'll try to subtract what we've accounted for basically by saying x squared plus 9 fits into there 4 times. We're gonna subtract 4 of these. So we're gonna subtract 4x squared, and we're gonna subtract 36. And it's going to cancel this out as it's designed to do. And we're going to have basically negative 36 left, which x squared plus 9 doesn't fit into, so it's just a remainder. And so now that has to be written, because it's a remainder, it has to be written just whatever it is, divided by x squared plus 9. Because we can't actually divide x squared plus 9 into it, so the best that we can do is set it up as a fraction where, like, you know, it's 36 on top and it's being divided by x squared plus 9, even though we can't actually, like, perform that division. We can write that operation, you know, as if we mean to do it, if we put it into a fraction form like that. Okay, so this is actually the integral of 4 minus 36 over x squared plus 9 dx. The integral of 4 is going to be 4x. And the integral of this minus 36, it's going to be minus 36 times, if you imagine, you know, just sort of taking that negative 36 like out, you'll have the integral of 1 over x squared plus 9. That's the same thing that it was here. It's going to be 1/3 arctan of x over 3. C, which you can simplify into being 4x minus, I guess that'll be minus 12 arctan of x over 3. Okay, so 3 integrals that look very similar in their integrands, but they end up looking pretty different to each other once they're actually integrated. And you know, just even a small change, like what power of x is on top, results in not like wildly different integration techniques, but pretty different from each other integration techniques. The first one just straight up fits a formula. The second one requires a u substitution, but it is possible. The third one, you can't do a u substitution. It's not just straight up one of the formulas that you already know, but by doing a little bit of algebra, you can rewrite it in a form to where, you know, you split it up into 2 terms, and then each of those 2 terms is just like a very regular integral, no u substitution necessary. Right. I did, right, there was that too. If you're wondering why, I mean, this isn't super important, but if you're wondering why x squared plus 9 doesn't have absolute value bars around it, that's just because x squared plus 9 will always be positive. So it would technically be redundant in this case specifically to write the absolute value bars, because x squared plus 9 is always going to be at least 9. The lowest that x squared plus 9 can be is 9, and that's if x is 0. If x is anything else, it's more than 9, but it's never negative, so there's just no reason to have the absolute value bars in this specific case. Yeah, okay. So these are
I mean, I don't want to call them tricks, right? They're not tricks. They're not some sort of oblique, esoteric knowledge that, you're just meant to pull out of a hat or something. These are techniques
For making something look different. Maybe making it more easily integrable. And we'll just, go through each of these, and then I'll just, we'll take a break, and I'll just leave this up here. Okay. So one of the more obvious techniques is if you have something that you can simplify, to simplify it. So if you have something like 1 plus e to the x that's all being squared, go ahead and square it. Go ahead and write, 1 plus e to the x times 1 plus e to the x, FOIL it out, come up with the three terms that it's going to be. Also just wanted to mention that this is not going to be 1 plus e to the 2x. Like, you don't just take a binomial and slap the squared on each of the two terms, and then that's what it is. There's going to be an entire middle term that you're going to miss if you just try to distribute that exponent to the two terms. And every semester, someone, like a couple people, end up, making this sort of mistake. Another technique is to separate a numerator. Now, don't try to separate a denominator. You can't do that. But you can totally separate a numerator if there are multiple terms in your numerator. Just set each of the terms over the shared denominator. So, for example, there wouldn't really be a great way to deal with 1 plus x on the top and x squared plus 1 on the bottom. A direct u substitution wouldn't be possible because, well, if u was the x squared plus 1, then du would be 2x, and you're not really going to get that out of 1 plus x. But if you split up the numerator, then, well, the part with the 1 on the top, that'll be an arctan, right, as you sort of saw from the comparison of, the three integrals earlier. And the part with the x on the top, that can be a u substitution. You just need, an extra 2 on the top, for it to be 2x, so that you can do that, so that it can be du, and you can use that u substitution. But you have to split it up first for that to be possible. Completing the square is, you'll generally be able to tell when you need to complete the square. If there's a quadratic, if there are some terms of a quadratic expression, but it sort of looks like there is a term missing, that's probably a good sign that you can simplify it by completing the square. If you have an improper rational function, and by that I mean, a rational function where the power on the top is at least as great as the power on the bottom. So, the numerator's power is greater than or equal to the power in the denominator. Then do the polynomial division. See what it comes out to. And that's, that's basically the third of those integrals that we looked at. It'll usually end up being some sort of whole number or, whole variable terms, and then maybe
a simpler rational term sort of at the end for if there's a remainder.
You can also add and subtract the same term in the numerator. You can't do this on the denominator. There's so much you can't do with denominators, but you're generally free to mess around with the numerator as much as you want. As long as it's mathematically justified. You can't just, if you put a +2, if you throw in a +2, you gotta throw in a -2. But other than that, you're entirely free to do that kind of thing. And the reason that someone might want to do that is if you look at the bottom here, that's x squared plus 2x plus 1. Now, it's probably a good candidate for u substitution, but if u is x squared plus 2x plus 1, the derivative of that, the du, would be 2x plus 2. And you only have 2x on the top. You don't have 2x plus 2. However, if you just straight up added 2, and maybe justified it by subtracting 2 right after, well, then you can split up the numerator. You can, after that, you can split up the numerator into one part that has 2x plus 2, which that's going to be a u substitution, and the part with a -2 on top,
that'll also be a u substitution, kind of. Really, it's going to be more like a power rule. And that's if you fold up x squared plus 2x plus 1 into being x plus 1 squared.
And the reason it becomes x plus 1 squared is just because, like this part right here, that's because a squared plus 2ab plus b squared is a plus b in parentheses squared. You can also use trigonometric identities. The most often used of which will be sine squared plus cosine squared equals 1. That's like the Pythagorean identity.
And other versions of that same thing where you got the terms on the other side or something. So 1 minus sine squared would be cosine squared, or 1 minus cosine squared would be sine squared.
But this is what those are all based on. And the other one that you'll see most often is that secant squared equals tangent squared plus 1. And there's a version of this that's basically the same, just with cosecant squared and cotangent squared plus 1. And you might have a different version of this where instead of a plus 1 with a tangent, you got a minus 1 with the secant instead. But it's like the same identity. So that would be good for if you had something like cotangent squared. You don't know the integral of cotangent squared. What you do know, possibly, is that cotangent squared can be rewritten as cosecant squared minus 1. Now, you do know the integral of cosecant squared. It is negative cotangent. That's just, one of those, that's just the reverse of some derivative rule that you already know. It's the reverse of the derivative rule for cotangent. So this cosecant squared would integrate into negative cotangent. Right? Yeah. And that minus x would integrate into, that minus 1 would integrate into minus x. And last, if you see something weird like 1 plus sine of x in the old denominator, you can try to get it to be some sort of some sort of meaningful trigonometric expression by multiplying and dividing by the conjugate. The conjugate being like just, the expression with the same terms, just a different sign in between. So you got 1 plus sine of x. The conjugate of that would be 1 minus sine of x, right? Same terms, different sign in between. And because you're trying to do that on the bottom here, you have to sort of justify it by also doing it on the top, right? So that you're really just multiplying by 1. You're not actually changing what the expression is, you're just sort of trying to change how it's written. So this denominator here, the 1 plus sine of x times 1 minus sine of x, that's, if you remember the difference of two squares formula where you have like a plus b and a minus b and you're multiplying them together, that's going to become a squared minus b squared. But even if you don't, you can straight up just FOIL it. 1 minus sine of x plus sine of x minus sine squared of x. And the middle terms in this case cancel out because one of them is positive and one of them is negative, but they're the same value otherwise. And so you end up with 1 minus sine squared. That's where that 1 minus sine squared comes from.
And the top is just, well, if you take 1 and you multiply it by something, it's going to be that thing. It's going to be 1 over sine of x.
Then what proceeds to happen is a Pythagorean identity is used. Sine squared plus cosine squared equals 1. So 1 minus sine squared is cosine squared. That's all that happens in that step. And then I feel like a step gets skipped here. But then this numerator is split up. So you can see that within this technique there are other techniques in this list that are like, applied in the process of doing this. There's going to be 1 over cosine squared minus sine of x over cosine squared of x. And this is 1 over cosine squared is the same thing as secant squared. Just because cosine and secant are reciprocal, so a cosine squared on the bottom means a secant squared, on the top. So if you were to integrate this now, this first term secant squared, that would simply become tangent. If you were to integrate it, just because secant squared is the derivative of tangent, so the integral of secant squared should be tangent. Then the sine over cosine squared, that would be a u substitution with u equals cosine and du equals negative sine. So it would end up being like 1 over u squared du, which you would integrate then using the power rule. Okay, I feel like it's been a while since we've done this, so take a 10-minute break and return at 9:22. Alright, so we got an integral with 2 terms in the integrand here. It's clear enough how to deal with this first term. That's just the power rule. So it's the line moved around last. Okay. The first one's going to be the power rule. You're going to raise the power by 1 and divide by the new power. The second one is not quite as clear, but it's actually also a power rule. However, it requires like a just tiniest u substitution to deal with first. And that's because instead of being z that's being taken to a power, it's actually minus z. I mean, technically 2 minus z, but like, that 2 is going to wash out in the, when you take the derivative to get your du. But because of that minus sign, that's just going to require the slightest of, u substitutions. Okay. So, if u equals 2 minus z, and that's how u substitutions go. Whatever is the innermost function you can find, that's probably your z. So, for example, u is not 2 minus z all to the 4th power. The u is just the 2 minus z that's in there, being raised to the 4th power on the bottom, but it's just that 2 minus z that's in there. So if u is 2 minus z, du is -1 dz, or just negative dz, whichever way you want to say it. But, if that's the case, then you can also just say negative du is dz. You can also do some weird thing where you like put a minus in front of the term and then a negative on the top of the term, but it's going to be the same result either way. So what I would do is split this up into 2 separate integrals, just so you can deal with them separately. One integral will be z to the 7th dz, and the other integral will be the integral of let's just say 1 over 2 minus z to the 4th dz for now. Okay. But if we've allowed this 2 minus z to be u, and according to this dz can be replaced by negative du. So if we do that, this will still be the integral of z to the 7th dz. We'll deal with that later. But if we make that u substitution, that's going to be minus from the minus du, as opposed to the plus that it was originally, minus the integral of 1 over u to the 4th du. Or, and you can totally skip to this step if you already know where this is going, minus the integral of u to the -4 du. Right, so once the u substitution is done, it's just a power rule. You're going to take both the first integral, the one that's in terms of z, raise the power by 1, divide by the new power, and you're also going to take the second integral, which is in terms of u, and raise the power by 1, divide by the new power. So actually integrating, that will be z to the 8 over 8 plus, let's see, if we raise the power by 1 on this u, that's going to be -3, right? -4 plus 1 is -3, and we're going to divide by -3, since that's the new power. So that'll end up giving us plus 1/3, or plus, whichever way you want to think of it, u to the -3 over 3. Actually, let me write it this way, it'll be better. U to the -3 divided by -3. That's probably a little clearer what's happening. So that's z to the 8 over 8 plus 1 over 3u cubed, right? Just send that u to the -3 to the bottom, where the 3 is, plus c, and finally get it all back in terms of z just by switching that u back. You can always, always switch your u substitution back after you integrate. So that's just z to the 8 over 8 plus 1 over 3 times 2 minus z to the third plus c. So obviously, if you were doing this yourself, and not trying to show a room full of people, like every sort of individual step, this can actually go pretty quickly. The second one looks daunting. First of all, because of a combination of x, an algebraic and a trigonometric function, and also just because of a pi, and also the fact that there's an x squared on the inside of this trigonometric function. So there are a couple things that make it look pretty bad, but it actually is not. This is actually just a u substitution. And again, in a u substitution, u is generally going to be the inside function of a composite function. So we'll see if 3 pi x squared wouldn't mind being our u. So if 3 pi x squared is our u, then du will be 3 is a constant multiple, pi is also a constant multiple. It's not. I mean, pi is a numeral, just like 2 or 4 or 7 is a numeral. And x squared, the derivative of x squared will be 2x, making this 6 pi x dx. Now, considering we already have the dx, obviously, and we also already have that x, that's in front, and all we need to throw in is a 6 pi, then this is starting to look pretty good. Now, of course, you can do sort of the same technique as we did before, divide out, I don't know, maybe 6 pi. I wouldn't, though. I'm about to do something completely different, but not really completely different. I'm just going to toss in a 6 pi over here and put a 1 over 6 pi on the outside. It's good to know, both ways of dealing with that sort of thing. Okay, so I want a 6 pi in there, so I'm just going to put 1 there. And I'm going to balance it out by putting a 1 over 6 pi on the outside. And so that's going to give me x times, cosine of 3 pi x squared dx. Okay, so this looks like a lot, but really, this is u. And what I now have here, this 6 pi x and this dx, together, make sure to definitely include the dx when you say this. These together are du. So what I really have to integrate is 1 over 6 pi times the integral of, well, that's going to be the cosine of u du. That's all the actual integration is the integral of a cosine, which is sine. So actually integrate this, and it becomes sine of u plus c, right? Because plus c once you integrate. So now just substitute u back, 6 pi, sine of, what was u? U was 3 pi x squared, so toss in that 3 pi x squared in for u. is. So, it starts off looking kind of bad, but it's, like super, ready for a U substitution. All it's missing is a 6 pi on the inside, which you can do relatively easily, as long as you put a 1 over 6 pi on the outside. But once you decide what your U should be, and then notice that you can get du as part of the integrand also, then the integral reduces to become something relatively simple, which I guess is kind of the whole point of U substitution. So that you can look at cosine of U du instead of having to look at cosine of 3 pi x squared 6 pi x dx. Alright, so okay. Integrating this, first of all, notice that there's an x squared on top and an x minus 3 on the bottom, so the degree of the top is greater. So, division is possible. X squared is the dividend, and x minus 3 is the divisor. X, the thing that starts off the divisor, fits into x squared x times. You would need to multiply by x to get up to being x squared. So it fits into there x times. And so we're going to subtract x of these. We're going to subtract x squared, and we're going to subtract negative 3x. So we're really going to add 3x. This is just, we're going to subtract x times x minus 3, which translates into being negative x squared plus 3x. Yeah. Right, we're just subtracting this number of these. And if you do that, then, well, you just get 3x, which, if you do that again, x fits into here 3 times. And if you then subtract 3 of these, you will be subtracting 3x and adding 9. And that's because you're subtracting 3 of x minus 3, which is minus 3x plus 9. Yeah. Okay, so the result of that is 9. No, that's not right. Right, these are the ones that cancel. Okay, and so you get 9 instead, or well, 9 as a result. Which I'll just go back to using 9. And now x can't go into 9, so 9 is your remainder, meaning that you're just going to have 9 over whatever you're trying to divide by, 9 over x minus 3. So this right here is like this, right? X squared over x minus 3 can alternately be written x plus 3 plus 9 over x minus 3. So this is actually the integral of x plus 3 plus 9 over x minus 3. You don't have to break this up into multiple integrals. The integral of x is going to be x squared over 2. The integral of 3 is going to be 3x, and the integral of 9 over x minus 3, a linear
term on the bottom and a constant term on the top, it's going to integrate into a natural log. It's going to fit sort of into a du over u kind of situation. I guess I will split them up. I mean, you really don't have to, but I will. 3 dx plus... In fact, I'm just going to write 9 times the integral of 1 over x minus 3 dx. I mean, you barely even have to think of it as du over u. It's just if u is x minus 3, then du is the same dx that would be there if it was just a plain x on the bottom. So like that, having that extra minus 3 doesn't really change anything. You just treat it like the same way you would 1 over x. But this is x squared over 2. This is 3x. And this is 9 times the natural log of the absolute value of x minus 3. Plus c. So no real u substitution here, although I guess you could think of that last term as a very simple and unnecessary u substitution. It's just divide the polynomials, get a bunch of different terms that are individually very easy to integrate. This one, might seem a little weird at first, maybe daunting. It doesn't look like a u substitution is going to work directly. If a u substitution were going to happen, it would probably be, u equals that bottom there, e to the negative x plus 1. But if that were true, and don't write this down, if u were e to the negative x plus 1, then du would be negative e to the negative x dx, which we don't really have. Yeah. So that's not going to really cut it. Well, let's say that we were going to multiply by e to the x on the top and bottom. So let's say 36, and we'll just put an e to the x on the top. And we'll also put an e to the x on the bottom. Right, so just multiply and divide by the same thing, basically. Well, if we simplify the bottom there a little bit, take this and distribute it here, e to the x times e to the negative x will be 1. For various reasons. You could say they have the same base, so you add the powers together, x and negative x, that's power of 0, e to the 0 is 1. You can also say that what's happening here is, well, e to the x is e to the x, and e to the negative x is 1 over e to the x, so that it just becomes, you multiply these two together, this is what it becomes, and so it's 1 that way. It doesn't really matter how you get there. All that matters is that that e to the x times e to the negative x is 1. And of course, e to the x distributed onto that 1 makes e to the x. And the top is still just 36 e to the x. Now that's looking a little bit better. Because dx. Because if you look at that now, if you allow what is now the denominator to be u,
if u equals 1 plus e to the x, then du is, well, the derivative of 1 is nothing. The derivative of e to the x is e to the x, and there's going to be that dx. Well, it looks like we have that du on the top. We have e to the x dx now. So that's looking pretty good. Let's just take that 36 to the outside. You don't really have to, but that'll make it look nicer. Alright, so this is u on the bottom here. This is du on the top. We have du on the top, u on the bottom, or 1 over u du, if you want to think of it that way. 36 times the integral of du over u, which is 36 times the, if you actually integrate it, that's the natural log of u plus c. And so here is the moment where you integrate. Which, if you switch u back to being in terms of x, that's 36 times the natural log of the absolute value of 1 plus e to the x, and then a plus c. So again, the actual integral itself is very simple. The only integral you have to do is the integral of du over u is the natural log of the absolute value u. So again, the actual integration itself is like so easy. It's just sort of getting it to look that way, or like recognizing what you have to do to get it to look integrable, basically. Then last we'll deal with this. This is a definite integral. We'll do it by hand first, and then we'll just do it by hand. Okay, so first, a direct u substitution will not work, but it is good to check for it, straight away. A direct u substitution won't work because if this bottom part, and usually if there is a u substitution, u will be, and you have like a fractional expression like this, u will be whatever is on the bottom, usually. But if u was e to the 2x plus 2 times e to the x plus 1, then du would be, let's see, the derivative of e to the 2x would be e to the 2x times an extra 2 because of the chain rule. So don't actually write this down though. So that'd be 2e to the 2x plus 2 times the derivative of e to the x would just be e to the x dx. Because the derivative of 1 would be nothing. We don't really have anything remotely close to that on the top. All we have on the top is e to the x dx. So this is not going to be the way to go. Not to say that it's not eventually going to be a u substitution, but it's just not going to be that u substitution. Okay. One thing you might notice is that, first of all, e to the 2x is going to be e to the x that's being squared, like e to the x times e to the x. That's how you get e to the 2x. So you might recognize this as, we'll say this first. So e to the x squared plus 2 times e to the x. I'm just going to put parentheses on here, plus 1. So you might notice that this is a form of a squared plus 2ab plus b squared, where a is e to the x and b is 1. Right? You got e to the x squared as your first term, you got 1 squared as your last term, and in the middle you got 2 times 1 times e to the x. So this is a plus b in parentheses squared. So this is really e to the x plus 1 as a binomial, like in parentheses squared. And so this is the integral from negative 4 to 1 of e to the x over the binomial e to the x plus 1 squared dx.
And now it looks like a different u substitution
is kind of possible. If we allow the inside of this function, just the e to the x plus 1, if we allow that to be our u, then our du can be e to the x dx, which we so conveniently have exactly in the numerator. And first, let me figure out something. If I take this substitution and I plug in my bounds for x, if I say x starts at negative 4, that's where my integration is, or integration begins. Well, if I plug in negative 4 into there, that's going to mean that u is e to the negative 4 plus 1. Not great, but
and again, you don't need to find these. I'm just doing this so that I have something to write for the bounds when it is in terms of u. Just because I don't want to be, I don't want it to be in terms of u, and then I'm still writing my bounds for x on the integral sign. That just wouldn't be right. And if x is 1, throw in 1 into here, e to the 1 is 1, so my upper bound for u will be e plus 1. Okay, so again, you don't have to find these out or use them if your plan in the end is to switch everything back in terms of x and just use your original bounds, like negative 4 and 1. Like, you don't have to do this then. But yeah, what was I going to say? Okay, so if e to the x plus 1 squared is, if e to the x plus 1 is u, and then this up here is exactly du. Okay, so we can rewrite this. We can write this as the integral from, and I'm just going to use my bounds for u now, e to the negative 4 plus 1 up to u equals e plus 1. Du over u squared. Right, it's in terms of u, so now I'm using my bounds for u. You can just write a question mark or something, or a number symbol, if you don't actually want to find them, but you want to still say that it's not negative 4 and 1. So this is actually u to the negative 2 du, which integrates, raise the power by 1, up to being negative 1, and then divide by the new power of negative 1. So this is actually going to be negative u to the negative 1, evaluated from e to the negative 4 plus 1 up to e to the, or e plus 1. Right, so the negative symbol is just there because you're going to divide by the new power of negative 1. So you can actually, if you found out these bounds for u, you don't actually have to change it back in terms of x. You can just say, okay, negative 1 over u alright. This is negative 1 over u. So I'm just rewriting u to the negative 1. It's 1 over u. Okay, so now if we plug these things in, it's negative 1 over e plus 1 minus negative, so plus 1 over e to the negative
4 plus 1. Which, I mean, that's an exact answer. I guess there are like ways that you could simplify it. You know, maybe write the e to the negative 4 as like 1 over e to the 4th, combine the things, resolve the complex fraction. But that's this should probably be good enough. Whatever value this ends up being. And that's it. That's the last one. So.